Hi, my name is Abdulaziz, and my paper is titled Anticipatory Bias Correction in Machine Learning Applications. This is a joint work with my colleague Chidansh and my advisors David and Vivek. Let me start with the motivation. One of the problems that is really associated to the fairness aspect is the problem of the distribution shift. Let me take an example. Let's say we have a distribution P, and from this distribution, we sample based on the IID assumption, and then we sample from different groups, for example, the blue and the red group, and then we have a training and testing. And if we build a machine learning model, we assume that the machine learning model will perform well for both these different training and testing sets. But in reality, this IID assumption is usually violated. For example, we might have a green group that our model has not seen before. So in this case, we do not suspect that our model will perform well with this green group, and also the fairness aspect will be also violated as well. The second aspect, which is a really a simple example, or maybe a type of this distribution shift, is the temporal shift problem. And in this case, we assume the same thing. We have a different individuals from different group, and then we could see that in the time t1, if we assume the time dimension, at time t1, we could have an equal represented individuals from different groups. But maybe at time t2, we could see that the red group is somehow shrinking due to some factors. And maybe at time t, we could see that the red group is significantly shrinking. And there might be suspected causes for this scenario. The first cause, maybe the machine learning model is affecting this problem or this cause, or maybe there might be a nature or maybe unknown factors that led to this problem. For example, in the first case, the model predictions maybe directly or indirectly affected society, and that will lead to a feedback loop. For example, the credit application or the predictive policing or language model applications usually have the same problem. The model will affect the society, and the society will be affected in this scenario, and this will lead to some groups not to be present in the distribution in the next cycle. And in the second cause, which is the nature or maybe due to some another factor, unknown factors, for example, the society changes by itself. So for example, the crime behavior, or maybe the college applications or applicant ratio with respect to gender is also changing. For example, the female ratios are applying to colleges compared to the male students. In this case, we call this problem a temporal shift, and this is what we address in this paper. So the main contribution in this paper, we wanted to show that the bias fluctuates frequently and is rarely stable, and also we wanted to show that the static learning is more likely not to perform well for both accuracy and fairness. The second aspect that we wanted to show in this paper, we propose a framework for the bias anticipation that can help us mitigate bias before it happens. And I wanted to emphasize on this last sentence that we wanted to mitigate the bias before we observe it, because in the current settings, usually we see that we could detect the bias and then we could correct it after it's observed. And lastly, because in this dynamic setting, we wanted to understand the bias dynamics, we proposed different temporal fairness metrics in order to address the bias dynamic. The past work that has done to address these problems, one of these solutions are the dynamic learning. So basically, you wanted to continuously train your model in order to address both the accuracy and fairness. And this solution is reasonable, but the only issue with this solution is that bias detection followed by a correction, and it's a reactive solution. So for example, we could observe the bias in our model, and then once we observe the bias, we could correct it in order to address this problem. And the limitation, as I said, the algorithmic bias gets detected after it has been observed, and this is a really a problem because in our example, maybe the red group will be experiencing some harm, and then the bias is reported, and then at the last step, we'll try to correct the bias in the model, and this is a really problem. And the second solution that we could use is the robust learning. And this is a proactive solution, which we wanted to prepare the model to any anticipated shift that we could suspect in the future. And the only limitation with this case is that not all changes are expected to be random. And I think this one, the solution is rarely suitable for the fairness aspect. So the method that we have proposed in this paper, the first thing that we assume that data arrives in batches according to a notion of time, because we wanted to address the temporal shift problem. And we utilize the dynamic learning paradigm to build a classification model. And we assume that at time t, we have an attribute x, and then we have a sensitive attribute a, and then we have the ground truth. And we use this one as a training. And then later we'll have a t+1, the same settings. We have the x and a and y, but we call this one a testing set. And in the temporal shift problem, we'll use the t step in order to address the training, and then we'll use the training, in order to test on the next cycle, which basically is the t+1. So the proposed framework for the settings, we have basically three main components or three main settings. The first one, we use a pre-processing method to address the algorithmic fairness. And the second setting, we use a retraining approach to address the distribution shift. And the main setting in our framework is that we use an anticipatory component to help us anticipate some knowledge about the future. So in our previous example, we wanted to estimate the relative ratio for the blue and the red groups in the next cycle. And if we were able to do that, we could somehow act accordingly before we train the model. And lastly, we use the temporal fairness metric to measure the bias dynamic. The first setting, or the first aspect, is the algorithmic fairness. We use a really popular method, which is a reweighting method. And basically this method will assign different weights to different people from different groups, and based on how they are equally represented in the data set. The second, or the main component in our setting, is the anticipatory component, or the anticipatory model. I wanted to emphasize on this setting is that we do not assume that we know the future data, but we know some knowledge about the future. For example, the relative ratios for the red group or the blue group in our example. And if we are able to do that, we could use it in our reweighting method in order to address the fairness aspect. So basically, we only use the aggregated knowledge, the macro properties for the future in order to address the fairness aspect. And we use the moving average forecaster, a simple method, in order to estimate the probability at time t+1 for the sensitive attribute and the ground truth. And to summarize, let's assume we have at time t, we have all the past data, and then we have observed that the red group is somehow shrinking. And based on this behavior, we could somehow infer what we could have in the future. For example, what the probability of a and y for time t+1. And then our framework will be, we'll use all the data that we have so far. We anticipate the probability for the future, and then we use an importance weighting method to have different weights based on the weight that we have so far and the weight that we suspect to have in the future. And then we use these different weights in order to train our model. And then later, when the data set gets observed, we'll use it to test, be tested on the future data set. And based on this setting, we assume that we will reduce the bias significantly compared to the other baselines. We use different metrics that have been used in fairness, namely the statistical parity difference, the equal opportunity, and the predictive equality. And also we proposed a different set of metrics because in our setting, we have the temporal fairness metrics scenario. So we proposed three different metrics. The first one is the maximum bias, which basically we wanted to see the worst case performance. And the second aspect in this set is we wanted to address the fluctuation in performance. So for example, we wanted to see how stable the bias is. And also we wanted to see the sudden fluctuation during the training for the bias aspect. For example, we have the temporal stability, and then we have the third one is the maximum bias difference. For the baselines, we have experimented with three different baselines. The first one is the vanilla setting, which basically we only train one for accuracy, and we do not address the fairness. because we only wanted to see if the bias is changing or fluctuating, or basically we just wanted to see the performance of the bias aspect. The second setting, or the second baseline, is the static setting, which is mostly used in fairness literature. For example, we train only once for accuracy and fairness, and then we deploy our model. And then the third baseline is the dynamic setting. We train dynamically for accuracy and fairness. And then our method, we utilize the dynamic setting, but we added an anticipatory component that will somehow help us to, will guide us to address the fairness aspect in our framework. And we experimented with 3 different data sets from different applications. And we emphasize on these aspects is that these 3 different data sets, they have the temporal aspect, they have time steps, but they have the time dimensions in the data set, because we wanted to address the temporal aspect. And also the sensitive attribute is different for each one of these applications. So for example, in the first one, we have the poverty level as a sensitive attribute, and then we have the gender, and lastly, we'll have the race. Here is one of the results that we have from the toxicity data set that we have used. And we report the average performance for all the time steps at the end of the training life cycle. So here we plot the accuracy on the left and the statistical parity difference on the right. So we could see that the vanilla setting will show us that the bias is not static, it's fluctuating, and it's not a static entity. And if we use the static training, which is usually used in fairness aspect, we could see that the bias is somehow reduced, but not significantly. We somehow reduce it, but still we have some issues in terms of the average, and the average performance, the bias is not reduced significantly. And if we use the dynamic learning, we could see that we improve the accuracy, but we could see that the statistical parity difference has reduced significantly compared to the first baseline and the second baseline. And if we utilize our method, which has the anticipatory component, we could see that our method is reduced the bias compared to the other baselines, and also it maintained the same accuracy with the dynamic learning. We also show that the data set with the different metrics that we have used, and also with different fairness metric, we could see that our method is mostly dominating other baselines, except in 2 of these cases. For example, the true positive rate difference in the toxicity data set, and also the false positive rate difference in the adult data set. But importantly, in the statistical parity difference, our model dominating other baselines. We also plotted the trade-off between the accuracy and fairness of these baseline. We could see that our method is dominating 2 of these cases, except in the true positive rate difference. We also reported all these results in the paper. And also we experimented with the temporal metrics. We could see that our method is dominating mostly all of these fairness metrics, but except in the maximum bias difference, we could see that the vanilla setting has the lowest maximum bias difference. But in 5 of these cases, our method is dominating other baselines. In conclusion, in this work, we examined the applicability of using early prevention to mitigate bias before it happens. And the main contribution in this paper, and we wanted to show in this paper, is basically we wanted to motivate others about the look ahead aspect, to anticipate changes and act accordingly. We do not want to wait until we observe the bias and then we correct the bias. Basically, we wanted to anticipate it, and then we correct it before we observe it. And also we proposed that a new temporal fairness metrics that we believe it's suitable for the temporally evolving settings. And lastly, we empirically validate our solution with the real world applications. And then the results show that there is a promise for the anticipatory bias correction in machine learning applications. Thank you for listening.